In this video for Computer Science 9618, we're going to take a look at a full Paper 3 walkthrough with all the explanations. This is Paper 3 Variant 2 from the October-November 2023 exam. So let's get started, and it's going to be mantissa and exponent. This is a very, very popular question that shows up on a lot of Paper 3 exams, and you can see it's 3 easy points to pick up. Real numbers are stored in a computer using floating point representation with 10 bits for the mantissa, 6 bits for the exponent, 2's complement form for both the mantissa and the exponent. That is the format that Cambridge uses. It may not tell you that 2's complement is being used, but you are expected to know that. Here they tell us. It says, write the normalized floating point representation of negative 96.75. And the key word you want to pick up on here is normalized. When something is normalized, the first 2 digits must be 0, 1, or it must be 1, 0. 0, 1 for a positive number, 1, 0 for a negative number. So we know the first 2 digits here are going to be 1, 0. When you have a negative number, it can be very hard to do negative 128 plus 64. Well, that would get us negative 64, and negative 128 plus 32. That becomes a real nightmare. So my advice to you is to do this. Find the positive representation of negative 96.75, which would be 96.75. Will 128 help get me to 96? No, it won't. What about 64? Will that help me get to 96? It sure will, so I put a 1 down. What about 32? Will that get me to 96? Yes, it does. What about 168421? I don't need any of those because I'm already at 96. What about 0.5? That'll help me get to 96.75, but then I need that 0.25. That'll get me there. Once you find the positive representation, all you need to do is follow the 2's complement rule. You're going to start on the far right. You're going to ignore all zeros until you get to the first one. When you arrive at the first one, you're going to keep it, and you're going to flip the rest of the bits. So let's start with this one. Well, we encountered our first one. We keep it. What do we do with all the bits after that? We flip it. This 1 becomes a 0. This 0 becomes a 1. This next 0 becomes a 1. All we do is flip those bits, and then at the end, where we have 1, 1, 0, that becomes 0, 0, 1. Now we have the negative representation of 96.75. When you are performing 2's complement, yes, you start from the far right, even at the decimals. You're going to flip everything. You're not just flipping everything to that's greater than the decimals. You're flipping the entire thing. Now that I have that, I can go ahead and fill in the mantissa. I want to make sure that I have 1, 0. In this case, I do. Let's say I had 3 more 1s out to the left of this negative 128. I would still move my decimal here, getting rid of those extra 1s. Now, right now, if my decimal is here, I'm at negative 128, followed by a bunch of values here. So if I wanted to get negative 96.75, I know my decimal needs to be here. I need to write the mantissa exponent representation. So all I do is fill in my mantissa with these numbers. 1, 0, 0, followed by 1, 2, 3, 4, 5 1s. 1, 2, 3, 4, 5, 0, 1. Now, my decimal is going to be right here. I need to get my decimal over here. I'm going to leave the decimal here. Now I'm going to show you where we need to move it. We need to move it right over here. Now when you write your answer, you're going to have the decimal stay here. You're not going to write it into 2 places. How do I get it from here to here? Well, I'm moving to the right. That tells me that the exponent value is positive, meaning it's going to start with the 0. Remember, 2's complement form for both the mantissa and the exponent. So I start with the 0, then I fill out another 0, and all I'm doing is writing the binary representation for 7 because I would have to move the decimal from here 1, 2, 3, 4, 5, 6, 7. And when you do that, you have your answer. Just make sure your decimal, you're going to leave it over here. I moved it to show you why we would have to move it 7 places because we're trying to get down to this representation. If my decimal's here, I show my exponent needs to move to the right 7 places. Continuing with mantissa and exponent, explain why a binary representation is sometimes only an approximation to the real number it represents. Well, you cannot represent all fractional parts of a real number using mantissa and exponent. You can get close, but it's not always going to be 100% exact. It works based on the powers of 2. You can get 0.5, 0.25, 0.125. You can get those. And you can only get close to a fractional part for others. Like, for example, you can't get to 0.3333 using mantissa and exponent. Your mantissa would need to be extremely, extremely large. So would the exponent. It would need to be very, very large so you could get to this. So that's why it's an approximation and never an exact. For this part of the question, when they talked about composite and non-composite data types, usually they're either going to ask you for the definition or they're going to have you work some out, assigning certain values to a specific composite or non-composite data type. So make sure you know how to do those as well. So let's start with composite. It's a user-defined data type that consists of more than one data type of multiple identifiers with the same data type. So they have one single name. All variables for this data type are under a single identifier name. So if we had students, we may create a structure, because remember in VB.NET, we don't have records. We create a structure. Well, under that structure, we could have a student name as a string, student ID number as a integer, student major as a string. So we have multiple identifiers with the same data type being that student info record. For non-composite, it's defined without referencing other different data types. They reference a single data type and only that data type. Now, it can be a single supported data type in any language, regardless of what language you're using. You have integer, you have Boolean, you have real numbers, you have characters, you have strings, or it can be user defined. So that's what you need to know for composite and non-composite. There's going to be a wide range of topics on the Paper 3 exam. Anything from Unit 13 all the way to Unit 20 could be on the Paper 3 exam. Sometimes they're going to ask you what things mean. For example, in the last question, composite, non-composite data, we simply explain what is meant by that. Other times, you're going to have to apply what you learned about the topic. And in this case, we have one of each. Outline what is meant by the term collision. So we have the location of a record in a random file is determined using a hashing algorithm. We should know that already. A collision may occur during the process of adding a record. Now, if you're enrolled in my class at our school, I had you guys hash your names where a collision happened, and then I had you figure out how can we still add to that data without overriding it. So all we're doing is taking that lesson that I set up in a very specific way and answering this question, picking up 5 points. So what do we mean by collision? Well, a collision is when two pieces of data, such as a student name in the example we used in class, go through the hashing algorithm and the result of the hash is equal. I take two different names, I hash them, they come out to the same result. Well, two separate pieces of data cannot occupy the same address on the RAM at the same time. How does it know where to go? Well, it's determined by the hashing algorithm. That determines where in the random file it needs to be stored. So how do we deal with that? Well, we start at the spot determined by the hash, and then we continue searching linearly for the next free spot to store the data. We're just going to keep going one by one, looking for the next available spot where we can store the data. An alternative way is to create an overflow area. When there's a collision, we simply go to the overflow area and we again perform a linear search from that spot we're at for the next open spot to store the data. Now, as soon as the open spot is found, the data is inserted. So that's what you need to know for collision and random files. Complete the following paragraph about a protocol suite using words from the given list. So we have BitTorrent and peer-to-peer. Those are related. We have queues, we have stacks. We know those are abstract data types. We have a link and star that could go together. We have a list that doesn't really go anywhere. And then we have a circuit switching, but we know that's a dedicated connection. But we're talking about the protocols in a blank determine the interconnectivity rules for a blank network model, such as the blank model. So we're talking about connecting together. So I know right away that's going to be a star, peer-to-peer, BitTorrent, or a stack, because those show the layers that are used. The protocols in a stack determine the interconnectivity rules for a layered network model, such as the TCP/IP model. Now, when you're talking about protocols, the TCP/IP has 4 layers that are organized in a stack. This is what they're referring to. These are the 4 layers of the TCP/IP protocol. Now, when you are sending data, you start at the application layer, move to the transport, the internet or IP layer, followed by the data link layer. So that is the layers visited in order when you're sending data. Say you're writing an email and you're in Gmail, that's the application. Then it's going to be split into packets. It's going to be given the IP address and the MAC address. Then you're sending that data. When you're sending data, it starts at application, moves all the way down to data link. When you are receiving information and information is coming into your network, you start at the data link, then you move up. So that's what they mean when they're talking about the layered stack of the TCP/IP protocol suite. Outline the reasons why an operating system may need to use virtual memory. So they want to know, do you know what virtual memory is, and do you know why it would need to be used? And then explain the circumstances in which disk thrashing could occur. Now, when you're on this topic, this is 16, which is purposes of an operating system. What does not appear on this paper 3 exam that you also want to review is the ready state, the running state, and the block state. Make sure you review that as well, because that could appear on the paper 3 exam. But when would we need to use virtual memory? Well, when the RAM starts running out of space or it starts to fill up. Now, it'll never be 100% full ever, but as it starts filling up and starts running out of space, it's going to start using virtual memory. Now, this could be caused by many, not programs, we want to say processes. Programs are simply code that is not running. A process is code that is running. It's not in, it is currently in the running state. So it could be caused by many processes running at once. And that's the word we want to use. We want to show Cambridge we know what we're talking about. When they see that word processes, if somewhere later down the paper 3 exam, if they say, the student may have misused the word, they may give you the benefit of doubt and give you an additional point, even though you didn't fully answer another question. So you always want to show the Cambridge examiner you know what you're doing, and we want to keep them in a good mood. That's just how it is. Now, if data from a process isn't used frequently, we can move it to the hard drive from the RAM. Now, when we do need to use it again, we're going to have to go to the hard drive and move it back to the RAM. But in order to free up space, we got to take something from the RAM, put it on the hard drive. Then we got to find it on the hard drive, move it back to the RAM. We need more pieces. So now we got to find something we're not using, move that to the hard drive, and then look on the hard drive for what we do need to get that piece off too. That causes disk thrashing. It could happen when virtual memory is being used. That's the only time it can happen. Data is moved between the hard drive and the RAM. Frequently, this causes a lot of wear and tear on your hard drive. When you talk about disk thrashing, we're talking about the hard drive. The swapping data back and forth from the RAM to the hard drive results in a lot of reading from the hard drive. There's a lot of rehead movements going back and forth all over the hard drive. More time is spent switching data back and forth from the RAM to the hard drive or the hard drive to the RAM than actually executing the process, which could bring your system to a very, very slow operating state or even to a halt. Now, you may have seen this. You get a message on your operating system where it says virtual memory is running low. At that point, you want to go ahead and start closing programs because you don't want to cause a lot of wear and tear on your hard drive. But that's what you'll need to know for these questions. The reverse Polish notation expression, RPN, may as well be free points that they're going to give you on the exam if it shows up on paper 3. I'm going to show you how to work this out. If you see any videos where they talk about, hey, here's a hack for paper 3. Here is the, the secret study formula for paper 3. Here is, what you need to do, the secrets for paper 3. There are no secrets. There are no hacks. There are no magic tricks. It's all about studying and implementing what you know. When you can understand the concepts, it becomes a lot easier. Now, there are study tips out there, and I suggest you use those, but you got to work hard. You got to study, and you're here working hard and studying. So let's talk about how we can easily figure this out, because it's not about taking a shortcut. It's about implementing what we know. So here we have AB times 2 divided by CD, divide, multiply, where A is 20, B is 3, C is 10, D is 5, and we have some stacks. Let's count how many things we have in our RPN formula here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 items in our RPN formula. How many stacks do we have down here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that a coincidence? No, it is not. All I'm going to do is underneath each stack, I'm going to write the value. What is A? That's the value of 20. I put that under the stack. What about my next item? B. I know B is 3. What about the next item? Well, that's a multiply symbol, the asterisk. I'm going to put all these under the stack. I keep going. I see a 2. I put that underneath. We have the divide symbol. I put that. I have C, which is 10. I have D, which is 5. Then I have another divide symbol and then the asterisk. So I had those, I wrote the asterisk symbol first. Now, I just want to be clear, you're not being graded on anything that you write underneath the stack. That is to make your life 1,000 times easier. If it's an operand, which is a number, you push it onto the stack. When you reach an operator, you then pop from the stack. Let me show you what I mean. Here we have 20. 20 gets pushed to the stack. So then I have 3. Now 20 is already on the stack. It's already there. But now I'm pushing 3 to the stack. Now I have reached an operator, the multiplication symbol. I need to pop these from the stack. Now it is not 20 times, or it's not 3 times 20. You may be thinking that, but it's not 3 times 20. It's 20 times 3. You may be saying, does that even matter? Yes, it does, and you'll see why in a moment. So I pop 3, I pop the asterisk, or I use the asterisk. I have 20. 20 times 3 is 60. I push that onto the stack. So 60 is pre-existing when I reach the 2. 2 gets pushed on to the stack. This is why it matters when you pop the items. Anytime you have subtraction or division, the order does matter. Because I can do 60 divided by 2 or 2 divided by 60, and those result in different operations. Now you may be saying, well, I'll do 60 divided by 2 because that just makes sense. What you need to understand is the 2 is popped from the stack first. Then I use that operator, which is the division sign. Then I put the 60. I do 60 divided by 2, and I know that equals 30. 30 gets pushed onto the stack where this division symbol is. I move on to the 10. Well, 30 is already there. I'm going to push 10 to the stack. I move to the next stack where the 5 is. Well, 30 is still there. So is 10. I push 5 to the stack. Now, we have divide. So I'm going to pop the 5. I'm going to use that division symbol. I'm going to pop the 10, and I have 10 divided by 5, which I know is 2. I push that onto the stack, but don't forget, 30 is still on the stack. the 10 and 5 just got divided. So now there's a 2 there. So now I'm going to pop the 2. I'm going to use the asterisk. I'm going to pop the 30. I'm going to do 30 times 2, which is 60. And that's what I write in the last stack. And just like that, I picked up 4 additional points on our paper 3 exam. Explain how an expression stored in RPN can be evaluated. All we need to do here is simply explain what we just did. We know that reverse Polish notation is evaluated from left to right. Now, each item is identified as either an operand or an operator. Now, your operand are your numerical values or your letters. An operator are your math operations, addition, subtraction, multiplication, or division. Now, your operands, which are not your math symbols, we push them to the stack. When we did encounter an operator in the stack, the most recent 2 items added to the stack, they're used to perform that operation. This is the 10 divided by 5, the 20 times 3. The result of the operation, when we figured out what that was, we pushed it back to the stack. And we kept repeating that until the end of the RPN expression was reached and we found out the final result. Here we have an interesting question because all we have to do is figure out the result of the NOR gate. Here we have the Boolean expression. Here we have the logic circuit set up for this Boolean expression. All I need to do is follow the rules for an OR gate and then invert those values. A NOR gate is simply an OR gate followed by a NOT gate. It is not a NOT gate followed by an OR gate. So when you see NOR, it's OR first, then inverted. If I put 0, 0, 0 through an OR gate, what's the value? Well, that value is 0. But then it hits this little small open circle here on the diagram. That inverts the value. What's the inversion of 0? Well, it's going to be 1. What about when I have 0, 0, 1? Well, that results in a 0 because when I put 0, 0, 1 through a regular OR gate, the result is a 1. But then it hits the inverter and becomes a 0. Remember the OR gate rules. The OR gate rules state as long as at least one value is true, and you can see in these next 6 rows, I have at least one value being true. When you put that through an OR gate, the result is 1. But then it hits this inverter. So all these that result in a 1 through a regular OR gate, they're going to hit this inverter, and they're all going to become 0. Here, we simply apply De Morgan's laws to the expression. We start with this A. What is that A? It's a not A. What about this plus symbol? We know that is a OR gate, but it says not OR. And you may be saying, that's a NOR gate. A NOR gate is an OR gate followed by a NOT gate. If I do a NOT gate followed by an OR, it doesn't come out to the same way. So I ask myself, what is not an OR gate? If it's not an OR gate, what gate does it have to be? It has to be an AND gate. And I do that with a simple dot. Then I look at the next part, this not B and the OR gate again. Well, I know it's not B, but what's not OR? If it's not an OR gate, it's got to be an AND gate. Then I look at the very last one, this not C. I put it down, and I have applied De Morgan's laws to that expression. I can also go backwards. Anytime I have not A and not B, that's equivalent to the same thing as A or B going through a NOR gate with a line over the entire thing. So going from a NOR gate to regular AND gates, going from AND gates, you can go back to NOR gates. So they could set this up either way. So just know it forward and backwards, and you'll know everything you need to know for De Morgan's law. Here we have a Boolean algebra problem, nothing that you can't handle. It says show all the stages in your simplification. So all we need to do is show what we're doing. We don't have to identify any of the rules that we use. Now, there are multiple ways to solve this. What I like to do is I like to start with the first 2 terms, see what do they have in common, and is there something I can do with those first 2 terms. So I look at the first term, I see there is a y in it. The second term has a not y. I can do something with that. So I'm going to factor out what they have in common, which is x and z, and then I'm going to have y or not y in parentheses. I can do something with this rule right here. Now, when you do that, you're showing that you're going in the right step. If you miss the next step, you're going to lose a point. You have to show what y or not y come out to. It says show all the stages in your simplification. A lot of students think that y or not y cancel each other out, and that's simply not true. They do not cancel each other out. When I have y or not y, that means all solutions work, because if y is a 1, it will work. That's one option. Or I could have not y, which shows y as a 0. So y can be a 1 or y can be a 0. Because either one of those will work, all scenarios work. So I show this as xz1. They do not cancel each other out. If I just write xz here and I don't show that it simplifies to a 1, I'm going to lose an easy point. Now, what's the rule when I have x and z and 1? Anything multiplied by 1 is itself. I get xz. So I show that stage as well. So now I've simplified these first two terms to simply xz. So I'm going to have xz or not x. Now remember, when you have complements, the one by itself wins. Cambridge loves to have Boolean algebra where this happens. It may not be x, y, z. It could be a, b, c, a, b, c, d. Just remember that when you have complements, the one by itself wins. What complements am I talking about here? What do I have? I have x and I have not x. The one by itself, we can say wins. Which one's by itself? The not x is by itself. That means this x over here on the left-hand side, it's out of there. It's gone. So we're left with z or not x. You could also write not x or z. Boolean algebra is pretty popular. It doesn't show up on every paper 3 exam, but it does show up from time to time. So you want to make sure you know that. I have a great video that walks you through all kinds of Boolean algebra examples. So make sure you check that out if you need help with Boolean algebra. Calculate the shortest distance between the start and each of the destinations, so that's A, B, C, D, E, F, in the diagram using Dijkstra's algorithm. Now, on the paper 3 exam, they could ask you about the A-star algorithm. So you need to know both of these. Another way they could assess you is to have you explain what Dijkstra's algorithm is, followed by what the A-star algorithm is. They could ask you, how does the A-star algorithm, how is it more efficient than Dijkstra's algorithm? And the A-star algorithm factors in or takes into account the movement cost. Here, we don't have movement costs. We simply have distances between the nodes. So we start looking at A. Well, to get from start, I can go from start to A, or I can go start to F to C to B to A. I can go from start to F to E to D to B to A. Those are the ways I could get there. When it says show your work, you want to put a 0 next to start to initialize that value. Now, we look at all the ways we can get to A. Well, here, there's a distance of 8. That's one way. And I can also go from start to F and start working in that direction. Well, that is 10. I don't need to go any further because I know 8 is less than 10. There's no point in even calculating the rest of it up because 8 is going to be less than the other way to go. So the shortest distance between start and A is 8. So I put that in the box. Now we look at the next one, B. How can I get to B? Well, I can go from start to A, which cost 8. I can go from start to F, which cost 10, but I haven't arrived at B yet. So I know when I go 8 to 4, that brings me a total of 12. If I go 10 and 7, that brings me to a total of 17. Well, I have arrived at B. If I decide to take the other route, 10 to 9, that's 19. I don't need to go any further because 12 is less than 17, but I also need to calculate the other way of getting there, which is start to F, to C, to B. Well, 12 is still less than 19. I don't need to calculate any further. So we put 12 in this box because I used 8 and 4. You add those two together, you get 12. Now we're moving on to letter C. Well, how can I get to C? Well, when I get to C, I can go from start to A, which is going to cost me 8, A to B, which is going to cost me 4, and then I can go from B to D, which it cost me 2. I can go from D to E, which cost me 2, and E to C, which cost me 3. When I add up those values, 8 plus 4 is 12. 12 plus 2 is 14. 14 plus 2 is 16. 16 plus 3 is 19. Now I have another option that will get me to C. I can go start A to B to C. 8 plus 4 is 12. 12 plus 8 is 20. That is not the shortest distance. Now there's another way to get there. I can go from start to F, that's 10. And then I can go from F to C, which is also 19. So I know I can go that way, but I can also go by going from start to F, F to E, that puts me at 17, and then E to C, which is 20. Now, because I have two pathways that equal 19, using Dijkstra's algorithm, because this doesn't factor in a movement cost, I simply just write down the value. I don't have to explain which way I'm going. Now, what if it asks me to explain which way I'm going? Using Dijkstra's algorithm, you can go in any way because the distance is the same. So here, we put in the value of, when we add all these values, 19. So those are the values we use because they are less than all other possible ways to get to node C. Now we're moving on to node D. All right, well, for node D, I can go start to A to B, then I can go B to D. That gives me a value of 14. I can also get there going from A to F, and then F to E, that's 17. I don't need to calculate anymore. There's no point in calculating the rest. I know that 8, 4, 2 is going to be the shortest route to get to letter D, and that is 14. Now, we're going to do the same thing for E. Well, I can go start to A to B, B to D, then I can go D to E. That brings me to a total of 8 plus 4 is 12. 12 plus 2 is 14. 14 plus 2 is 16. That gets me to E. When I check start to F, we see that is 10. And then when I go F to E, that brings me to 17, which is not less than 16. I don't need to calculate the rest of it. I don't even have to calculate this 9 over here because I know 7 is less than 9, but the shortest distance is going to be 16. Now we have to do F. Well, I see the distance between start and F is 10. I don't even need to bother calculating the rest of these because I know by now start to A is 8. When I calculate the 4, that's 12. I know 10 is the smallest number, and that is how you use Dijkstra's algorithm. It is that easy to pick up 5 points. So the abstract data type that they chose for this paper 3 exam, also known as ADT, was a stack. Now there are 4 abstract data types you need to know. Not only do you need to know how they work, you need to be able to program them because one of those 4, or these 4 that I'm about to give you, will show up on the paper 4 exam most likely. That's going to be a stack, a queue, a linked list, and a binary tree. You want to know the differences between those 4. So it says a stack, an abstract data type, is to be implemented using pseudocode with procedures to initialize it and push new items onto the stack. A 1D array stack stores the contents of the stack. So it says study the pseudocode in part A2 and complete the table of identifiers by writing the missing data types and descriptions. You should know right away the difference between a base pointer and a top pointer without having to look at the pseudocode for a stack. Now, the base pointer, it's going to be an integer. It's always going to be an integer because it's pointing to the index of the array. It points to the bottom of the stack. Now the top pointer is also an integer. It's used to point to the top of the stack. You need to have a top pointer so you know the next item to be popped because stacks follow the last in, first out principle. And then we have the identifier, the variable named stack, which is of the real data type, and that's used to hold real or decimal numbers in the stack, because that's what real data type is. It deals with real numbers or decimal numbers. Here is the pseudocode. So we have a constant, max size equals 40. We have base pointer as an integer, top pointer as an integer. Then they have a stack as the array. They're using index 1, going to index 40. And what data type is it made of? It's made of real, which are decimal numbers. Now we need to initialize the the pointers. So it says initialization of the stack. You don't have to initialize anything with the array. You need to set the value of the base pointer and the top pointer. Now, because it's using index 1, that's why they have 1 and 0. If they use index 0, they'll also use the value of -1. Now, our base pointer is going to be 1 because index 1, which is the very first part of our stack or our array, that's going to be the end of the stack. That's the bottom of the stack. It's right there at the very end. Now, the top pointer, they initialize to 0. That's to show the stack is empty. So there's nothing that has been added to the stack. That simply sets up those pointers. Then it says push an item onto the stack. So we have a procedure called push, accepts new item as a real data type. So that's going to be the new item that we're adding to the stack. The first thing we have to do is check, do we have room in our stack? Well, we got to make sure that our top pointer is less than max size, because the max size is 40. If my top pointer is already at 40, you can't say, yep, we're good to go. No, that's the stack's full. We don't have any room. So this is why it's if top pointer is less than, not less than or equal to. If we have room, then what we need to do is we need to increment the top pointer by 1. That says, okay, we are going to move it to this index. So if I'm at 39, 39 is less than 40. I'm going to move the pointer to index 40. So when I do stack 40, what am I putting in there? Well, what value was passed down to this procedure? That's new item. I'm going to put that into the stack. If we want to make a stack, we can use an array, but here they want to say, can you justify the use of a linked list instead of an array to implement a stack? Well, an array is static and it's a fixed size. We have to determine what the max size of the array is. With a linked list, I don't have to do that. It's dynamic and can be updated either adding or removing nodes. If I need to add a node, it will simply adjust the size. If I remove a node, it will adjust the size, and we call that dynamic. Now, when adding or removing items, pointers are used, but more efficiently than an array because you don't have to move items into or out of the array. When you pop an item, you simply remove it from the linked list. You update the pointers accordingly. If you add an item, you erase, you figure out where it goes, erase the pointers, and just readjust a couple pointers. You're not moving data around, so it's a lot easier using, or more efficient, I should say, than using an array. All right, in part C, explain how a compiler makes use of a stack when translating recursive programming code. They want to know, do you know what recursion is? So when you call a method, the compiler starts running through all that code. Eventually, it may reach a statement where the method calls itself. And that's what a recursive method is. It's simply a method that calls itself. When the compiler reaches the recursive call, it says, okay, let me stop here. I'm going to take the current call that I'm on. I'm going to put that over here onto the stack, and I'm going to start working on this new recursive call. Starts going through the code, encounters another recursive call. It says, let me stop where I am. I'm going to take this one. I'm going to add it to the stack over here where the other one was, and I'm going to keep working on this one. Well, that keeps happening until the base case is reached. So the results of a recursive call are pushed onto the stack each time a recursive call is made. And we call this winding. We keep winding until we reach the base case. When the base case is reached, the calls and the results that are in the stack are popped from that stack using the last in, first out method. So the very last item that was added to the stack before we reach the base case, that's going to be popped first. So the computer is going to handle it using the last in, first out method. So it's very important to understand that. Now this implements what is known as unwinding. Once you reach the base case, it's now time to unwind to find the result of the initial or original call to the method. Because in order to solve the original or initial call to the method, You have to work through the entire stack to get those preceding values to figure out what the original value or original call was. Another way they could assess you on recursion, they could give you some simple pseudocode with the trace table, have you find the final value using recursion. Another way they could do it is simply ask you, do you know what recursion is? They could show you pseudocode and have you identify what statement in the code or what line of code makes it recursive. They may ask you what abstract data type does a recursion use, and it always uses a stack. Those are the various ways they can assess you on recursion. Describe the features of the SIMD and the MISD computer architectures. This shows up in Unit 15 in the same unit where RISC and CISC shows up. There are 4 computer architectures. There's SISD, there's SIMD, MISD, and MIMD. Now, they can assess you this a couple different ways. The way they have chosen to assess it this time is by writing down how they work or describing the features of them. Another way they could assess this is to put a couple of these or all 4 of them and have you match to descriptions. I like this because we get a little more freedom and we're not locked into how Cambridge wants to say it. So SIMD stands for single instruction, multiple data. You will get no points if you write single instruction, multiple data. That is what it stands for. I have that on here so you know what it's referring to. So let's describe the feature. It carries out the same instruction, that's what we mean by single instruction, the same instruction through an array of processors on different data sets. And that's what the multiple data refers to. So we have the same instruction. It's going to be the same across all processors, but each processor is working on a different data set. Now, the MISD stands for multiple instructions, single data. So each processor is working on the same data set through multiple processors that are independent of one another. So they're working on the same set of data, but they're each following their own set of instructions because we have multiple instructions here. We have an array of processors. However, they're working independently of one another rather than together as a whole working on the same data set. Now we get into declarative programming. One of the best pieces of software to use is Prolog. It follows this extremely closely and it does declarative programming. So if you're looking for a piece of software to use that's very close to this, Prolog would be the IDE that you are looking for, and it is free, which is great. So doing these just a couple times, you'll pretty much get the hang of it. They're pretty easy to do. So here we see some hobbies. Music is a hobby. It tells you, they're always going to tell you how it's read. Natasha is a person. Natasha enjoys traveling. Toby dislikes caving. And I don't blame him because when you go caving, you can wind up getting stuck. I've seen all those claustrophobic videos. And even though I'm not there, it does give me a little bit of anxiety. But anyway, let's see here. Carlos is a person who enjoys the hobby of cycling, but does not like music. Write additional clauses. And that's what these are. These are clauses to represent this information. So the first thing I need to handle is that Carlos is a person. I look over here. How did they handle it? They used person, then in parentheses, they put the person's name and they put a period. Now there's a reason it is all lowercase. One of the number one mistakes students make is that we're so used when writing people's names, we write it as a capital. It's very important that you do not do that. We need to make Carlos a person. And when you make Carlos a person, you got to put a period at the end. That is a stop command. If you do not put the period, you're going to lose a point because it needs a stop command for the clause. When you make the period on your paper or the dot, make it a little exaggerated so they can clearly see it. They're not going to try to figure out, did you put a dot there? They're not going to zoom in and try to figure it out. So if you need to exaggerate it a little bit, feel free to do so. So that takes care of Carlos as a person. Now we need to say that Carlos enjoys the hobby of cycling. Well, he can't enjoy the hobby of cycling until we add the hobby of cycling. So cycling is a hobby. Again, we have that stop command all lowercase here. Now we can say that Carlos enjoys cycling because look at the enjoys. Natasha enjoys traveling. So here we're going to do enjoys. Carlos enjoys cycling. Again, with a period for the stop command. The last thing we need to do is the dislikes. Carlos dislikes music. And just like that, we pick up 4 points on the declarative programming section, part 1. There's another part that comes up next. If declarative programming is assessed on your paper 3 exam, you're going to have the first section usually followed by this next question. Now, I told you that it needs to be all lowercase. Why is that? Because anything that is uppercase, a single letter, or an entire word, that is a variable. So to answer this question, we need to refer back to this. Using the variable P, the goal, P enjoys camping. It's going to find, P is a variable, it's going to find everybody who enjoys camping. Well, it's not Natasha, it's not Toby, it's not Nina. It's Elijah. It's not Fatima. It is Joseph. It's not Toby, so that's why it prints out Elijah and Joseph. This order does matter because as it's going through, it's going to print Elijah, then Joseph, not the other way around. Write the result returned by the goal enjoys, or P enjoys climbing. So Natasha enjoys traveling, so not her. Toby enjoys climbing. Nina enjoys climbing. Anybody else? Nope. So who do we output first? We put Toby followed by Nina. So the P refers to the names Toby and Nina. So when we look at line 14 and 15, we see they enjoy climbing. The P references the name because the P is the first thing in parentheses. Well, what's the first thing in parentheses here? Those are the names. Again, make sure you put this comma and make sure Toby and Nina are lowercase because they are actual names, not variables. Writing your rules for declarative programming, such as if statements, they can be a little challenging, but you can do it. All you need to do is break it down because this does involve some critical thinking and logical reasoning, and you're able to do it. N is a person who might enjoy H if H is a hobby and N does not dislike H. Write this as a rule. So here they've written it in what you would see in Prolog, and then we have to write the rules for that. So they always give us the word if. Well, the first thing I need to do is I need to break this down and figure out what I need to do. Well, I need to make sure that N is a person because it says N is a person. So the first thing I want to check is that N is a person. If N is a person, I need to make sure that H is a hobby. That's the next thing I need to do. If N is a person, H is a hobby, and I need to make sure that person N does not like or does not dislike the hobby, because if they do dislike it, they're not going to want to do it because it says N is a person who might enjoy. So here's what I do. All 3 have to be true, so I need to use the keyword and here. Person N and hobby H and not dislikes N, comma H, that is the rule. That is my if statement. If all those things return true, then I know it may be something that they enjoy. I'm checking to see that Carlos is a person, the hobby that they might enjoy is a hobby, and then he doesn't dislike it. Now, another way you could do this, you can replace these ands with commas. Now, you still want to use the word not, but the ands you can replace with commas. What I always tell my students to do is use the keyword and in all caps because it's a lot easier to read, and that way you don't make a mistake. But that wraps it up for declarative programming. Describe with an example what is meant by an exception. An exception is a runtime error that happens when your program is running. You've been programming since pre-ACE or even AS, if that's where you started. We have all had our programs throw exceptions. When we open a file, we want to do that inside a try-catch statement. That's called exception handling. So we do a try-catch statement to prevent our program from crashing and outputting a message. We're trying to prevent it from throwing an exception. Now, this can be caused by trying to access an index that's out of range, probably the very first time, and even still now, when you're working with an array, you may be indexed out of bounds or indexed out of range. You're not in between the lower bound and the upper bound. It's a very common mistake. dividing by 0. Maybe you ask the user, hey, input 2 numbers. What do you want to divide by? They enter 5 and they enter 0. Your program's going to crash. It's going to throw an exception because it doesn't know how to divide by 0 because that's undefined. What about storing data into a wrong data type or any other runtime errors? Maybe I have a real number, 3.14. Maybe I want to store that as a Boolean. Computer's not going to know how to do that. It's going to throw an exception. So an exception is any runtime error where your program crashes, and you can pick any example you want. I use some common examples that I see all the time. But let's go ahead and get ready to move on to the next question. A pseudocode algorithm searches for a customer record in a random file, accountRecord.dat. So when you get on your paper 4 exam, you'll have to handle a txt file. You will not have to handle a data file, which is .dat. If you do have to handle anything like that, it will be on paper 3, and that's what we see here in this example. The records are stored using the user-defined data type taccount. This is an example of what we call composite data. It's all under a single identifier, taccount, and we have different data types here. We have integers and we have strings, and then we have int type. So we need to keep that information handy. So when we look at the question, which is this right here, we can fill it out. This is worth 7 points. And if you stop, take a deep breath, it's very easy to work through. Now, after we handle this question, I want to talk about some things that do not appear on the paper 3 exam that could appear. So if you're looking at the time, you're like, oh my God, does it take that long to answer this question? It does not. But I want to talk about what doesn't appear on this test that could appear on your paper 3 test. But if you found this video helpful so far, just take a moment to give it a thumbs up and subscribe to help the channel grow. But let's go ahead and go through this question. If the record is found, it is output. Otherwise, an error message is displayed. Complete the file handling pseudocode. So we have customer as taccount. That refers to all of these, or account number, name, address, telephone. We have location, which is an integer. Now the location is going to refer to where in the file that a piece of data is stored, and that's done by a hashing algorithm. We have max size, so it's only going to hold a certain amount of data, it looks like. Found flag. A flag just determines whether it was found or not. That's a Boolean. We have search customer, so we're going to be looking for somebody, and their max size is 1,000 here. So we need to open the file. What file are we opening? Well, it tells us the file accountRecord.dat. Well, why am I opening it? Because remember, it's open file accountRecord.dat. You want to put that in quotes for what? For random, because it's a random file, not a txt file. So if you do for read, that's with the txt file. We're opening it up as a random file. We set the location to 1. What are we going to set the false? Well, there's only one Boolean value that we can set to false, and that's found flag. So already we're about a third of the way through. Now enter the customer's name. Well, that's going to be the customer we are searching for. So that's simply input search customer. We're inputting that value into this variable. Now we're looking for something and location is less than equal max size. So we're looking for this and we're looking for this. We're not looking for this and location to see if those are less than equal to max size. We're looking for location less than equal to max size and something else. Why would we be checking to see if location is less than equal to max size and something else? Well, we want to make sure that the found flag is false. So while not found flag, meaning found flag is false, and the location is less than equal to max size, then we know we can keep looking through it. What keyword do we look through to say, I want to search through accountRecord.dat? We're going to use seek. We're going to seek the accountRecord.dat. Where are we looking? We're looking at the location that we're currently at. If the search customer, what the user inputted, is equal to the customer.name, then we're going to say customer found. We output customer. We set the found flag equal to true. We end if we increment the location regardless of whether or not this is found. Because if it's not found, we still need to increment the location. After we exit this while loop here, it says if not found flag. So if found flag is false, then we know that customer doesn't exist. Now we need to talk about some things that did not appear on your paper 3 exam that you need to be ready for. Now there are several items that did not appear on this paper 3 walkthrough that we did. We didn't see anything about creating a record. They asked us about composite data instead. You need to know how to be able to create a record. We didn't see anything at all about BNF. BNF syntax diagrams, those are extremely popular questions. We didn't see anything about it. We also didn't see stages of a compiler, which ties into BNF. We didn't see anything about solving a recursion problem. All they did was simply ask us what recursion was. We didn't see anything on JK flip-flops. We didn't see anything at all about CISC or RISC or pipelining, and pipelining ties into RISC, which is reduced instruction set computing. We didn't see anything about the programming paradigm differentiation. Sometimes they'll ask you, what are the different programming paradigms and describe them? Well, you have procedural, which is writing a standard program. You have object-oriented programming. You have declarative, which we did today. You also have low-level programming. So those are the 4 paradigms. We didn't see anything about the process states. We didn't see anything about running, ready, and blocked. We need to know those process states. We didn't see anything about how computers or the operating system handles interrupts. We didn't see any questions on virtual machines. We didn't see anything about the guest and host operating system there. We didn't see anything about symmetric and asymmetric encryption. I thought that was very interesting because those have been pretty popular in the past. We didn't see anything about quantum computing. And yes, this test at the time this was recorded was given a year ago. We didn't see anything on artificial intelligence. Artificial intelligence is part of the mainstream now. It's part of everyday life. I would be surprised if AI wasn't on the exam from here on all the way until the end of 9618. AI, I'm almost positive, is going to be on there. We didn't see anything about sorting methods. We didn't see a bubble sort. We didn't see an insertion sort. We didn't see a 2D array bubble sort. We need to be familiar with those. They could have us write pseudocode for that. We didn't see anything on digital certificates for websites. Today we saw Dijkstra's algorithm, but we did not see the A-star algorithm. We did not see machine learning with back propagation included. That goes along with AI. We saw stacks and linked lists, but we didn't see queues. We didn't see binary trees. Oh, we also didn't see K-maps. I didn't list that here, but we didn't see K-maps. I was very surprised. Usually when you see Boolean algebra, K-maps is going to be a given. We didn't see any pseudocode written for object-oriented programming. We didn't see any diagrams either showing inheritance, containment, or aggregation. We didn't see any of those diagrams. Now, if you have a pseudocode handbook that your teacher or instructor gave you, or if you're doing self-study, make sure you have the newest pseudocode handbook. It does include, at the very end, object-oriented programming. That's in the new pseudocode handbook, so make sure you have that. It's very close to how we program in VB. You make all the attributes private, so you do like private name, colon, string. So it's very, very close to how we code in VB. We didn't see anything on big O notation. We didn't have to evaluate the different efficiency of algorithms, and we didn't see low-level language. And yes, even though that's a programming paradigm, sometimes they will give you trace tables where you have to work out the low-level language, and you have to identify various things with labels, and those can be worth quite a few points. Anyway, that's some of the things we didn't go over that I've seen in other paper 3s. Don't be afraid to check out other paper 3 exam videos. I have a few on my channel. You can ask as many questions as you want, so if you have a question, please post a comment below, and I'll do my best to answer your question. That's what I do for a living. 6 of the 7 periods that I teach a day are computer science. So I love it. I'm very passionate about it, and I am willing to help you. All you got to do is ask. So please don't hesitate to ask. It's not a problem at all. I'll be more than happy to assist you because I am an educator at heart. So thanks for checking out the video. If you did find it helpful and you haven't yet, please take a moment to give it a thumbs up and subscribe to help the channel grow. Good luck on your exam, and we'll see you guys in the next programming video.